Hi AP Stats, this is 5.3 notes, part 2, and today we're going to work on conditional probability and independence. So the last thing we were working on in 5.3 and 5.2 was the idea of having the and or the or connector in between two events. Today we're going to focus mostly on the and connection between those two events. So first thing is independent events are two events that knowing that one happened does not affect what the second one happening. Okay, so that basically the definition says when knowledge of one event does not change the likelihood of another event that will happen, we say that the two events are independent. Now there's a formula for this that says the probability of A given B should be the same probability of just A by itself, right? If they're independent, taking it as a subset of B shouldn't make any difference. It should be the exact same amount because A has nothing to do with B. So the probability of A should be the probability of A no matter what. Okay, so, and then the reverse of that, the probability of B given A is equal to the probability of B. So same deal there, probability of B should be the same regardless of what it is given that goes with it. So here's a couple examples. And our first one, we're looking at a table that is looking at the length of somebody's hair and whether they have pierced ears or not. Interest, A is the length of hair, B is the pierced ears. So they want to know are length of hair and pierced ears independent events. So to look at that, we're trying to find out is the probability, and we can pick any single one of these, right? So I'm going to pick one of the hair ones. So is the probability of having long hair going to be the same thing as the probability of having long hair given that they have pierced ears? So I tend to pick out the ones that are the yeses when I do these. So I could have just as easily said is the probability of pierced equal to the probability of pierced given long hair, okay? All right, so probability of long hair, that is the total. So that is 90 over 178. Okay, and then over here, it's a given that, so I've got to find out where my totals are for pierced, that is 103. And of those, which ones are long? That's those two. So I'm going to go and figure out, oh, this one's more than half and the second one's less than half. I do not think they are equal. If they were the same probability, we'd say they're independent. So what is this one saying? They're saying that this one is less likely to happen than this one, more likely to happen. So long hair and pierced ears are not independent. Matter of fact, we know that if someone has pierced ears, they are less likely to have long hair. Which I guess it kind of makes sense. If you have pierced ears, you probably want to show them off. You probably don't wear your hair that very long. Maybe, okay? So that's basically the only test is you just have to know how to test for independence. It's a probability thing. Now, if you don't have probabilities or it's just something where they're just giving you the two events and they're not giving you tables of numbers, then you have to go back to the original definition. Does knowing that the first event happened change the probability of the second event happening? Like flipping a coin. Does knowing that I got a heads the first time have any effect on me flipping the coin the second time? No, so then those are independent events. Okay, let's take a look at number 12. So it says, suppose we randomly choose students and recorded their handedness, whether they're right-handed or left-handed. And the events of interest are A, gender, and B, handedness. So look at the table below. Okay, so are they independent events? So let's go check. Is the probability of, you want to do right-handed? Let's do right-handed. Is the probability of right-handedness equal to the probability of right-handedness given that they're female, given that they're male, right? It doesn't really matter here. Let's go with given that they're female. Okay, so again, I'm basically just taking the first ones off of each row. So the probability that they are right-handed is 225 out of 300. And the probability that they are right-handed given that they're female means I total the females first and then I do right-handed is 150. Okay, so I'm going to have to go down to decimals to see if these are the same thing or not. 225 divided by 300 is 0.75, and 150 divided by 200, I'm pretty sure, yep, is 0.75. So what that means is the probability that I get of people being right-handed is the same regardless of whether they're male or female. I'm getting the same amount. So I'm not more likely to be right-handed if I'm female. And then I could check it again for right-handed if they're male and do the same thing there and say that right-handed and male should be the same numbers as well. So let's just go check just to show you. Okay, so I'm going to redo this one. I'm going to do probability of being right-handed, we'll keep that one, is equal to the probability of being right-handed assuming you're male. Okay, so this one will still be the same, 225 over 300, 0.75. This one will now be the total males, which is 100, and then I want the ones of them, look at that, 0.75. Okay, so I don't really need to do every single one of them. I just really need to pick one from the column, one from the row, and then check them against each other. Awesome. On to the next one. So that means that we also are going to come to the idea of two events. And again, the main idea here is if A and B are independent events, then the probability that A and B both occur is just A times B, right? Just one versus the other. If they weren't independent, they would look something like this underneath, which is A and B is the probability of A happening, and then the probability of B happening, assuming A already happened. Okay, that would be a conditional one. So for an independent, we don't have to worry about A having already happened because we already know they're independent. So I can take off that given that A happened beforehand. Okay. All right, so let's do a couple examples that have general multiplication rules. So in baseball, a perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. Historically, pitchers throw a perfect inning. An inning is where no hitters reach base about 40% of the time. So to throw a perfect game, the pitcher needs to have 9 perfect innings in a row. What is the probability that the pitcher throws 9 perfect innings in a row, assuming that the pitcher's performance is independent? So they already gave us is independent, okay? So because they're already independent, I just have to do the first thing and then the next thing and then the next thing. So what's the probability of getting a no-hitter in the first inning? It is 0.4. And then the next one is 0.4 for the second inning. And then for the third inning is 0.4. And we're going to keep doing that until we get all the way down to the 9th inning, 0.4. So I can think of a faster way to write this. This is 0.4 to the 9th power. Okay, so when I raise it to the 9th power on my calculator, let's see, here's what I get. I get 2 ooh, hello, where did that come from? Let's go back. I get 2.62144 E negative 4 on my calculator. Now this is really important. When you see that E negative 4, that's scientific notation. Negative numbers means it's smaller than it looks. Positive numbers means it's bigger than it looks. So that it's smaller by 4 decimal places means I'm going to have to move that over 4 different places. So I'm going to do 2.62144. I'm going to start it right here. I'm going to go back 1, 2, 3, and 4, and that's where my decimal should go. So that is the probability of pitching a perfect game, if assuming that their pitching was truly independent, which we know there's some fatigue and stuff like that. So we're just taking the perfect cases here. So if they're independent, we'd be looking at less than 1%, less than 1/100th of 1%, right? We'd be looking at thousands, 10 hundreds, thousands, 10,000s, right? We're looking at 2 10,000ths of a percent, all right? On to the next one. A test is given to diabetic patients to determine blood abnormalities. Approximately 5% of diabetics will show abnormal results. If 100 people with diabetes are tested for blood abnormalities, what is the probability that at least one patient will have abnormal blood results? So again, we'd have to do this 100 different times. So here's what that would look like. So the probability of at least one, and at least one abnormality, is the probability that there's exactly one abnormality and then 99 that are not, plus the probability that there's 2 abnormalities and 98 are not, plus all the way up to the probability that all of them have the abnormalities. And I would have to add all of those probabilities together. Okay, so that's an awful lot. the only thing that's missing from this number line is the probability that none of them have abnormalities. So this one's actually easier to figure out. What is the complement of this? So the complement of this is equal to the probability that it never happens, right? That's the only number we were missing. We started at least 1. That already included 1. So the only thing left is 0 we didn't use. That should be doable. So let's go see if we can figure that out. So the probability of none being abnormal is not abnormal would be 95% for the first person and for the second and for the third, right? Because there's no abnormalities. 5% of them are abnormal. So if I want none of them to be, it would be this idea to the 100th power. Okay, now that's not really what I want. They didn't ask me for how many had none. They asked me for how many had at least. So I'm going to end up doing 1 minus 100% minus the 1 probability that wasn't included. So that would be 0.95 to the 100th power. Now, if I grab my calculator and go do this, let's see what that would be. I'm getting that it is 0.0059, which would be 0.991. So that is how many, the likelihood that at least one of the patients will have that abnormality, 99.41%, that at least one of the 100 will have that abnormality. It might be more than 1, it might be 2 or 3, right? But there's a very, very small chance that none of them have it, right? So again, it's that same idea. You just keep multiplying each one after the other, and if they're independent, the number should stay the same every single time. On to the next part. All right. So here we're going to talk a little bit about one setup and using our formulas to help us. So in the first one, they gave us 2 events. They didn't even tell us what they are. They just told us the probability of them. So the probability of A happening is 6%. The probability of B happening is 78%. Okay. And they said, if that's already given to you, if you already know that, what is the chance of, what is the probability if they're mutually exclusive? So remember, mutually exclusive means that if I draw a Venn diagram, there's no place where it overlaps. So A is over here, B is over here. That's different than an independence question. This is just the mutually exclusive question. So if that's true, they're telling me it should be the probability of the first one, 0.06, plus the probability of the second one, 0.78, plus the probability of the intersection, the section of the Venn diagram that they both exist in. Well, there's nothing here, right? So this is plus 0. So if things are mutually exclusive and they're asking me to find both events happening, we can just add the probabilities together. So this is going to be 0.84, I think. All right, same setup. A is still 6, B is still 78. Now we're going to look if they're independent. So remember, independent is just a separate question. Independent just says they have no memory. So again, we can start out with the probability of A is 0.06. The probability of B is 0.78. Now, in independent, there might have been an overlap. So how do I go and figure that one out? Well, I know that the probability of A and B is equal to the probability of A times the probability of B given A, right? Probability of A and B, if, right, is one plus multiplied by the other. So this would be 0.06 times what? Let's go see. Times B, given that A already happened. But in independence, we don't have any of that knowing that something happened, right? So if they're independent, this would really just turn into the probability of B. So we would multiply this by 0.78, and we would get 0.0468. So this last part is minus 0.0468 would be the overlap, okay? And that would turn out to be 0.7932. Okay, so remember, we just used this one. I just took the one that had the conditional part on it and then said, oh, they're independent. It doesn't have conditional if it's independent. All right, to determine if 2 events are mutually exclusive, okay, we already know, once you know that they're mutually exclusive, they are not independent. They are actually dependent on each other. This is one of the big rules that will always exist in probability. So it's one of the first questions we always ask. if you are doing a problem yourself and they're asking you about is it mutually exclusive or is it not, or is it independent, you always want to ask the mutually exclusive one first, because you are basically just looking for, if I drew a Venn diagram, would there be an overlap? If there's an overlap, they are not mutually exclusive. Okay, so let's show you an example of that so you kind of get the idea. So let's say we're talking about the grade in an English class. And obviously I need work with that because it should be earning a, not and a. Okay, earning an A and a B in English class. Are they mutually exclusive? Could you earn an A and a B in your English class at the same time? The answer is no, they're apart from each other. So now that I know they're mutually exclusive, I know that they cannot be independent. So let's talk about why I know that. So it's not independent. Okay, so let's say I had an A. So let's say I'm standing in there. Well, knowing that I'm standing in the A circle already tells me I can't be standing in the B circle. So knowing that the A already happened already is giving me information that the B cannot happen. So I am getting extra information between the two events. So the second that you know it's mutually exclusive, you're either in one circle or the other, that those are not independent. Yet once you know that you're in one circle, there's no way for you to be in the other circle. So we already know a little bit more about what happens next once you know one thing has already happened. So if events are not mutually exclusive, which means there is an overlap, then the question becomes, does knowing the probability of the first event help me to know the probability of the second event? So we're looking for stuff like with replacement, then it's probably independent. Without replacement, it's probably not independent. Given that, well, that usually is wording that we see when things are conditional, so not independent. If no memory of prior events, then it's probably independent. So some things that are independent can be mutually exclusive or not mutually exclusive. So we have kind of every combination going if you are going from independent the other way. So let's take a look. All right, so let's take a look at some of these other ones. Now, in this first one, I'm not really happy with it. So bear with me here, we might change a little bit of this because we're only tossing a die once, right? That's what they said, we're only tossing a die once. So I don't understand how event A could be the first toss and B could be the second toss if we're only tossing this once. So can we just say event A is going to be named and event B is going to be named in the problem? So we're just going to call this event A and event B. Okay, so in our first one, we have that the event A is while I'm throwing that die once, the probability of me throwing it and it being a 3. Event B is the probability of me throwing a 4. Are they mutually exclusive? Well, yeah, if I only throw the dice once, it can't be a 3 and a 4 at the same time, right? It's either a 1, it's a 2, it's a 3, it's a 4. So this is what your Venn diagram would look like, right? Each one would be its own. So it is definitely mutually exclusive because in one throw of a dice, I cannot get a 3 and a 4. Okay, but we still agree that it's independent, that if I throw a die and it's fair die, every time I throw it, it shouldn't have any memory of what it had before. Let's try the next one. So now this one, event A is toss a number less than 3, and B is toss a number that is an odd number. Okay, so let's take a look at this one. If I throw the dice once, could it be a 3? Could it be a number less than 3 and also an odd? Yes, there's some overlap happening there, right? It could be a 3, it could be a 1 for the overlap, that's less than 3 and an odd number, right? So in the less than 3 category over here, we could have the 2. And then over here, it said toss an odd number. We could have the odd numbers over here. So less than 3, and then the odd numbers over here would be 3 and 5, and then the other numbers would be outside the circle from our die. So that would be like 4 and 6 would be out here. So that is definitely not mutually exclusive, right? And again, it's still the same idea of just tossing a die. So that is an independent event, right? Okay, so on these, we're going to go through some practice, same as what we just started, okay, of can you decide whether these items are mutually exclusive or independent, and how do you decide, right? So remember, our first question, question number 1, every single time, is you're going to ask the mutually exclusive one first, because it's a little bit easier for us to imagine the idea of a Venn diagram overlapping than it is to think about the independent stuff. So I'm going to pick one card out of a standard deck, Event A is that that one card is red. Event B is that that card is a club. So first question is it mutually exclusive? This is where I'm going to start. Could I have it be a red club? No. That means they are mutually exclusive. So this is the red section. This is the club section, right? So they are not mutually, or sorry, they are mutually, sorry about that. They are mutually exclusive. And this is the one that automatically goes to, therefore they are not independent. The second that I know it's a red, I know it can't be a club. The second I know it's a club, it can't be a red. So knowing something about one event does tell me something about the other event. So that is not independent. And that is always the direction it goes. Once you know it's mutually exclusive, it is not independent. All right, let's try the next one. Roll one standard die and flip a coin. So now we're doing two different things. So now my sample space is going to look something like this. A 1 and a heads, a 2 and a heads, a 3 and a heads, right? And then I'd have a 1 and a tails, a 2 and a tails, a 3 and a tails, dot, 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 all the way down to 6 and 6. Okay, that's what my sample space looks like. All right, so event A is rolling a 3 on the die. Event B is the coin being tails. Could I have both happen? Well, I could have it happen because it shows up in my sample space. So again, in between, we have one of them being rolling a 3, roll a 3, right? And then the other one is what's on the coin, coin being a tails. So we would have a 3T here, and then all the other T's would go here, 1, 2, 1T, 2T, 4T, 5, and 6. And over here would be all the 3s, so the only other 3 would be 3H. Okay, so if they're overlapping, they are not mutually exclusive. I'm going to start abbreviating this as ME in a second. Not mutually exclusive. And then the next question is, now it could be independent or not independent. Does, when I roll the die, give us any information about whether the coin is going to be heads or tails? No, right? It doesn't make any sense. So these are independent. Okay, so we can have both happen at the same time, not mutually exclusive and have it be independent. All right, so here's another one. Event A is that there's heavy traffic. Event B is that you're late for work. Okay, are the events independent, mutually exclusive? How do you check? So could I have heavy traffic and be late for work? That sounds like it could be an overlap. So traffic and late. Here's all the other days where I just had traffic, but I wasn't late. Here's all the other days I was late, but didn't have traffic. Okay, so I think that this is not mutually exclusive. Okay, so now comes the independent question. Does knowing one happen affect the other? If you know it's going to have heavy traffic, do you think it affects your probability of being late for work? Yes, right? So these are not independent. So again, I'm just looking at, does one affect the other? Does knowing one tell us anything about the other event? Right? And then in D, it says pick one card out of the standard deck. So again, just one card. Event A is that the card is red. Event B is that the card is a heart. So we've learned now the first thing you ask is, can I have a red heart? Yes. Matter of fact, I can have 2 in a standard deck of cards, right? I could have a diamond, right? And I could have a heart. Okay, so if it, so the overlap, I take that back, would be just the heart, right? So in between, this would be red, this would be hearts, right? And we could have a red and a heart. Matter of fact, they'd be kind of overlapping. Aren't all the hearts red? But not all the reds are hearts, right? So it almost look more like this. Red carries both the hearts and the diamonds. So it'd almost be like this. This side of it is hearts. And the big circle is red. So I could definitely have both. It'd be this section in here that is red and heart. So all the hearts are red and would be the overlap section. Okay, so are they mutually exclusive? Definitely not. So not mutually exclusive. Okay, are they independent? Does knowing that the card is a heart give you any information about whether it's red or not? Absolutely. Does knowing the card is red give you any hints about whether it may be a heart or not? Absolutely, because now I'm not thinking about it can't be any of the black cards. Once I know that, I know it's either a heart or a diamond. That's a higher probability than all the other cards. So this one is not independent. Okay. Hey, that's it. We're done with this one. Cool. All right, so we'll see you next time. Bye.